Section 1.3 looks at the basics of functions. So when two phenomena are related to each other by a rule of correspondence, we call this a relation. For example, the area of a circle, which we'll call A, is related to the radius of the circle r by the formula A equals pi r squared. If you want to find the area, you would need to square the radius multiplied by pi. That's how they're related to each other. When a relation matches each item from one set to exactly one item from the different set, the relation is called a function. So here's a real life example that I think makes it easy to understand what a function is. So an example I'm going to talk about is a birthday, or birthdays, I should say. If set A is all the people in our class and set B are all the days on a calendar, I could start by saying, let's say Ben's birthday is June 3rd. Let's say Mac's birthday is February 7th. Let's say Colton's birthday is April 10th. And let's say AJ's birthday is also April 10th. If I was connecting these, I would show the relationship for what was paired with what by drawing lines. Okay. Every person in set A, obviously there's more people in the class, and it goes beyond the class, but every person must have a birthday. There's no person whose name I could put here where I wouldn't have a connection to a date. Every person must have a birthday. In set B, I'm going to have all the dates of the calendar year. Obviously, someone was born on every day, but it could be possible if they added a new day to the calendar that no one was born on it yet. So it's okay if there were numbers here that didn't have. If we were just talking our class, it might be the case that no one was born on May 27th. So no A would be drawing to B as May 27th. It's okay that Colton and AJ share a birthday. People can have the same birthday, but one person cannot have two birthdays. For example, Mac's birthday cannot be June 3rd and February 7th. So every person has one birthday. People can share a birthday. So our x values are the domain, and our y values are the range. So here are our characteristics of a function when we're talking from set A to set B. So order does matter here. So each element in A must be matched with an element of B. That's the case of everyone has a birthday. Some elements of B may not be matched with an element of A. That's that idea of if we added one more day to the calendar, for even if it was minutes, no one will be born on that day yet, and that's okay. 3, 2 or more elements of A may be matched with the same element. That's saying that people can share a birthday. However, an element of A, which is our domain, cannot be matched with two different elements of B. One person cannot have two birthdays. So keep in mind, A is our people, B are the dates. And our function here is the function of a birthday. That's the example that I'm using. If it doesn't make sense, we can talk about other examples, but I think that seems to be a pretty clear example for people. However, when we're looking at a graph, we can determine if something is a function by using the vertical line test. So I'm going to show you what that looks like on a graph. If we're not looking at a graph, you need to make sure that every x has only one y. So basically, if I can write it as a y equals, I'm good to go. Okay, that tells me it's a function. If your calculator can graph it, you can type it into y equals. That's what your calculator knows. Your calculator can only graph functions. There are ways to trick your calculator into graphing things that aren't functions. You can trick your calculator into graphing a circle. But a circle is not a function. You can never write a circle as y equals. Okay, so I'm going to show an example of both of those situations. So we look at these and we say, are they functions? If I'm doing the vertical line test, I start, and anywhere that I draw a vertical line, I want it to only pass through my function once for that vertical line. So these all pass at one spot. The parabola passes. It is a function. Think about it. You can put that in your calculator. It'll graph a parabola. However, a circle is not a function. It passes in two spots. Not a function. Does not pass the vertical line test. All right. Let's look at this where I have the XY chart written out. I'm looking to see that every x has only one y. So basically, do my x's repeat? In this case, my x's do not repeat. I notice that 0 goes to 7 and so does 4, but that doesn't matter. That's two people sharing a birthday, so I'm good to go. That's still a function. So yes, this is a function, and my reasoning would be no x's repeat, or every x only matches with one y. However I wanted to write that, however I wanted to show, I'm going to have to provide explanation, so that's going to be my explanation. Okay, let's go on to testing algebraically. So what I'm looking for here is, can I get the equation as y equals, right? Remember, your calculator can graph a function. So if you can get it as y equals, it is a function. So I'm going to subtract x squared from both sides, and I get y is equal to negative x squared plus 1. This is a function. Yes, I could get it as y by itself. For b, if I move the x to the other side, I'm looking at y squared is equal to x plus 1. In order to get y by itself, I need to take the square root. So y is equal to the square root of x plus 1, but I have to keep in mind when I take a square root like that, my answer could be the plus or minus. Because that's the case, there's no plus or minus button on your calculator. This would have to go in as two separate, the positive square root of x plus 1 and the negative square root of x plus 1. This is not a function for that reason. The plus or minus makes it not a function. When we're talking about function notation, how we're going to say these things so that we sound like we know what's going on, the input, which is our x, is our independent variable. Doesn't matter what we put in, but our output is y, and that is dependent on what we put into the equation. Some people like to think of a function as a machine, right? Your function, you have f of x here. That's the function. You're going to drop in your x's, and out comes the y. Okay, the function only works in one direction. Okay, so when we see this notation, this f and then parentheses x, we say f of x, or the function evaluated at x. But you don't say f parentheses x, you say f of x, or the function evaluated at x. This is called function notation. So how we write functions, how we talk about functions, is a specific set of rules so everyone's on the same page. So let's talk about how we evaluate a function. This might be some review, some refreshing, but regardless, we're going to do a few examples. So when we evaluate a function, we're taking the value inside the parentheses and plugging it in anywhere we see the variable in the original function. So if I'm doing g of 2, or the function evaluated at 2, I'm plugging in 2 anywhere I saw an x in the original function, and then simplifying. So 2 squared is 4, but I want the negative, so negative 4 plus 8 plus 1. 8 plus 1 is 9, plus negative 4. I would say g of 2 is equal to 5. That would be my final answer there. So then I would evaluate the next one. G of t, literally all I would do is, instead of writing an x, I write a t. That is the function evaluated at t. I'm just changing the variable. So my last one, g of x plus 2, instead of writing x, I plug in x plus 2 anywhere I saw an x in the original. I could simplify further if I wanted to, which I'm going to just to make a note. X plus 2, here we go, note. This is a very common mistake. X plus 2 squared is not equal to x squared plus 4. X plus 2 squared is equal to x plus 2 times x plus 2. So I'm talking about x squared plus 4x plus 4. You have to FOIL there. You have to use the distributed property. So when I simplify that, I'm looking at negative, I'm just going to distribute the negative to all of those, negative x squared minus 4x minus 4, I'm going to distribute this 4, plus 4x plus 8 plus 1, and this whole thing simplifies to negative x squared. My 4x's cancel out, negative x squared plus 5. So g of x plus 2, or the function evaluated x plus 2, simplifies to x squared plus 5. Just by eyeballing it, g of 2, which was 5, plus g of x, if I added 5 to this original right here, I would get negative x squared plus 4x plus 6. Notice that's not the same as g of x plus 2. So g of a, this is generic, plus g of b is not equal to g of a plus b. So we just saw that example, like this is what we looked at. G of 2 plus g of x is not equal to g of x plus 2. That's the example we just worked. But it's valid for any of those numbers that we're going to be plugging in, for all numbers there. All right, let's take a look at piecewise functions. Piecewise functions is basically two functions smashed together, okay? So this part right here, these are our parameters telling us where the different functions apply. So for any value less than 1, or less than 0, I'm sorry, we're going to be using this function. Any value greater than or equal to 0, we use this function. So when I evaluate at negative 1, I'm going to use this function because I'm talking about a value less than 0. So the function evaluated at negative 1 is equal to negative 1 squared plus 1. I use these piece right here, to determine what function I'm going to plug into. That's where I start when I'm talking about a piecewise function. So negative 1 squared is 1 plus 1. F of negative 1, the function evaluated at negative 1 here is 2. So now I'm also going to evaluate the function at 0. I start here. I'm going to choose this one because that's when x is greater than or equal to 0. So I'm going to plug in f of 0 is equal to 0 minus 1. So f of 0 is equal to 1. I'm sorry, negative 1. We're going to talk about how to graph piecewise functions a little later in the year. We'll also talk about domain and how to apply the domain in class.